Hello again, glad you're still with me. Today we're going to talk about the notorious X-Wing pattern. In Sudoku, all the various solving techniques fall into a few categories like loops, chains, uniqueness tests, coloring, subsets, wings, and believe it or not, fish. We will be covering all of these things and more in future tutorials. But oddly, there is something called a turbo fish, which is not really a fish by definition, it is actually a chain. And likewise, the X-Wing that we are going to talk about today is not really a wing by definition, it is actually a fish. Go figure, right? Anyway, those of you who have watched all of my previous videos know that I sometimes use modified names for certain things that I feel are more descriptive than the standard ones. But since names like turbofish and X-Wing are so widely used, even though they are somewhat misleading, we will stick with tradition on these and several other well-known solving techniques when there's not a compelling reason to deviate from the norm. But just know that an X-Wing is really a fish by definition, which I'll get to in a minute. Okay, let's go over to the puzzle board and see what an X-Wing looks like and how they work. Just like locked candidates, fish are what's known as single-digit patterns. Single-digit meaning they focus on only one candidate at a time, like all threes or all sevens, for instance. And pattern means the candidates lie in a specific recognizable configuration in relation to each other, as opposed to a chain which can snake all around the puzzle with no definite shape. And learning to recognize these patterns is crucial to your becoming a Sudoku expert and being able to apply all the solving techniques that are based on those patterns. Fish are constructed with what are called base sets and cover sets, and the number of sets determines which type of fish it is. There is always an equal number of base sets and cover sets. When there are two base sets and two cover sets, it is called an X-Wing. If there are three base sets and three cover sets, it is called a swordfish. 4 is called a jellyfish, 5 a squirm bag, 6 a whale, and 7 a leviathan. I will cover swordfish in video number 12, and I will cover jellyfish in my advanced series. I will not be covering squirm bags, whales, or leviathans because these larger fish will always have within them a smaller fish that you can solve first, which means it is a complete waste of time and energy to look for fish of size 5, 6, or 7. And I will not be covering complex fish like frankenfish, mutant fish, and Siamese fish because the same eliminations can generally be made by using other much simpler single-digit patterns like turbofish, two-string kites, skyscrapers, and empty rectangles that we will be learning soon in videos 14 through 17, or by other various chains and loops that we will study and learn in later videos. But I will be covering what's known as a krakenfish in my advanced series because they are a breed of their own. I used to say kraken, but I looked it up and the correct pronunciation is kraken. A krakenfish is a Norwegian sea monster, which is pretty cool, and this is how they say it in Norway, so we'll stick with that. In any event, don't worry, we are going to eventually cover everything you will need to solve any Sudoku puzzle. All right, back to today's business. The explanation of the logic behind X-Wings using the standard base set and cover set perspective or reasoning is, in my humble opinion, a little convoluted and hard to understand. So I'm going to quickly explain this concept to you, but then I'm going to show you what I think are some much better and much easier ways to think of them, identify them, explain them, and prove them, okay? A normal X-Wing has 2 base sets and 2 cover sets. A set is simply a house, and for an X-Wing, it can only be a row or a column and not a block. Each base candidate can only appear in one base set. This simply means the base sets cannot overlap. The cover sets must overlap or intersect with the base sets, and the cover sets must cover or contain all the base candidates. An X-Wing, or any size fish, will always have an equal number of base sets and cover sets. Therefore, if the base sets are 2 rows, then the cover sets will be 2 columns that intersect with them like this. And if the base sets are 2 columns, then the cover sets will be 2 rows that intersect with them like this. And because in an X-Wing there are only 2 cover sets that have to cover all base candidates, that means there can only be 2 base candidates in each one of the base sets. Got it? So in each base set, one of the base candidates must be true. But each base candidate also lies in a cover set. This means that one of the base candidates in the 2 intersection cells in each cover set must be true. Therefore, you can eliminate all the same digit candidates from the cover sets that are not in the intersection cells, i.e. that are not base candidates. See what I mean? Sounds confusing, huh? It's a bit cryptic to be sure, but I would be remiss as your teacher if I did not explain this to you. So let me try to demonstrate what this means and how it works, and then immediately afterward I'll show you some much easier ways to understand X-Wings. In an X-Wing, it turns out that the base sets are simply 2 conjugate pairs that lie in either 2 parallel rows or 2 parallel columns. And these 2 conjugate pairs have to line up perfectly so that the 2 cover sets can intersect with them like you see in this diagram. So the base sets here are row 3 and row 7, and you can see that there are only 2 instances of candidate 3 in each of those rows. So that means in row 3, one of those 2 threes has to be true and the other has to be false. And the same applies to row 7. One of the 3s has to be true and the other has to be false. Now the cover sets here are column 4 and column 7. And they also contain those same 4 candidate 3s that lie in the yellow intersection cells. So we know that only 2 of those 3s can be true and the others have to be false. And the only way it's going to work out is like this. Either the one in the upper left is true and the one in the lower right is true like that, and the other 2 will be false, or the one in the upper right will be true and the one in the lower left will be true and the other 2 will be false. This ensures that one of the 3s in those 2 columns in the yellow cells must be true, and therefore you can eliminate all other candidate 3s from the 2 columns that lie outside the intersection cells. Let's first take a look at column 4. Because of the 2 conjugate pairs in row 3 and in row 7, we know that one of the 3s in the yellow cells in column 4 has to be true. The one in row 3 column 4 or the one in row 7 column 4 must be true because of the base sets containing those conjugate pairs. So that means you can eliminate all the other 3s in that column that lie outside the cell. So you can eliminate that 3, and that 3. Now let's look at column 7. The same thing applies. One of the 3s in the 2 yellow cells has to be true because of the conjugate pairs that lie in row 3 and row 7. So you can eliminate that 3, and that 3, and that 3, and that 3. And you could eliminate a 3 in any one of those light blue cells if there was one there. So there can be up to 14 eliminations with an X-Wing. The intersection cells will always form a rectangle or a perfect square, which makes it pretty easy to spot. Those 4 yellow cells, that's the X-Wing. An X-Wing will always have 4 intersection cells containing the fish digit. And it will turn out that 2 of those digits in the intersection cells will be true and the other 2 will be false. And so, of course, the 2 digits that are true will always be on a diagonal with each other, across the rectangle or across the square, even though we don't yet know which diagonal pair is true. But it makes no difference. We don't need to know which diagonal pair is true. We can still make the same eliminations because of the X-Wing. In your mind, if you can draw two imaginary lines connecting the two sets of diagonal cells, you will understand where this pattern got its name, because those two crossing lines will form an X. So now let's take a look at what happens when the base sets are in the columns and not the rows. Here we see we have two base sets in column 3 and column 6. They each contain a conjugate pair of two candidate 7s. So we know that in column 3, one of those two 7s must be true and the other must be false. And in column 6, one of those two candidate 7s must be true and the other must be false. So this time, what we just did in the last example is kind of turned on its side to the left 90 degrees. So you have to be able to look and find these either way, whether they're in the rows or the columns. This one, the base sets are in the columns. So that means either this candidate 7 is true and that one is true and the other two are false, or this one is true and that one is true and the other two are false. So what that means is that we can eliminate every other candidate 7 from the rows this time, because the base sets are in the columns. So we can make the eliminations in the rows. So we can eliminate this 7, that 7, that 7, and that 7. And we can eliminate that 7, that 7, and that 7. And remember, you can make an elimination out of any one of those light blue cells if it contains a 7. In these first few diagrams, I am just showing the candidates we are focusing on so we can zero in on them. But in real puzzles, all those cells containing the 7s, or any other fish digit, will always have additional candidates in them. Otherwise, you would have a naked single, and there would be no need to find these fish patterns. Okay, so now you've seen how the base sets and the cover sets work, and you've seen how the conjugate pairs work. But let me show you two more ways to prove the logic of these X-wings that will help you understand them even better. So let's go back to the diagram with the 3s, and let's remove these colors. All right, now let's take a moment to review what we learned in video number 4. We know that if we have an open-ended alternate inference chain that begins and ends with the same digit, meaning a type 1, we know that any other same digit candidate that can see both ends of the chain must be false, because one of the endpoints of the chain must be true. And that's exactly what an X-wing is. It's an alternate inference chain if you look at it in a different way. So let's start on this 3 right here, and remember, blue to yellow will be strong and yellow to blue will be weak. So from this 3 to this 3 is a strong link. There are only 2 3s in row 3. Then from this 3 down to this 3 is a weak link, and then from this 3 to this 3 is a strong link. So here we have an alternate inference chain of 3 links. The 2 endpoints are in the same house. So that means any candidate 3 that can see both endpoints of the chain must be false. So that means this one is false, that one is false, and that one is false. Now, we can go and do it the opposite way. We can start with this 3 down here in the bottom. If this is a strong link, and that's a weak link, and that's a strong link, it's the same thing. If the bottom one is false, the top one is true. And in the first chain, if the first one was false, the last one was true. So one of those 2 3s in column 4 has to be true, so every other candidate 3 that can see both of those will be false. And because they lie in the same house, that means every other candidate up to 7 instances of that candidate can be eliminated as false. And now let's do it the other way. If we start on this 3, we go, there's a strong link to the 3 over here because there are only 2, and that's a weak link, and then a strong link. So there you have strong, weak, strong. So every other candidate 3 that can see both of those endpoints over here in column 7 can be eliminated as false. So isn't that cool? All you do is you look for a square or a rectangle that's formed by 4 instances of the same candidate that looks like that, and either you have a strong link in the rows or you have a strong link in the columns, and you've got an X-wing. Here, it's the 2 rows. And that's what you look for. You look for a rectangle or a square that contains two parallel strong links. And then if the strong links are in the rows, you make the eliminations in the columns. And if the strong links are in the columns, you make the eliminations in the rows. All right, let me show you one more way to look at an X-wing. As it turns out, an X-wing is the simplest form of what's called a continuous loop. Now this is kind of an advanced subject, and we'll be learning more about continuous loops much later on in the course, but I think you can handle this right now. A continuous loop is a chain that's just like an AIC that alternates strong, weak, strong, weak, strong, but instead of having an odd number of links, it has an even number of links because it has to loop back to where it starts. And if you had an odd number of links, then you'd have two strong links in a row or two weak links in a row, and it would not be a continuous loop. So let's take a look at this X-wing right here, and we'll see that here's the series of links. Let's start on this top left 3, and there's a strong link to this 3. That means if the first one is false, the second one is true. And if the second one is true, then this one down here is false. And if this one is false, because this is a strong link, if this one is false, that one is true, and now we go back, right back to the beginning, and if this one is true, that one is false. So you can just keep going around in a circle. If this one is false, this one is true. If this one is true, that one is false. If that one is false, that one is true. That one is true, that one is false. And it's just a continuous loop. And now let's start on this other 3 in row 3, this blue one up here in row 3, column 7. And if we start there and say if that one is false, then this yellow one is true. If the yellow one is true, the blue one down here is false. And if that one is false, the yellow one is true. And if that one is true, the blue one up here is false. So what this means is that either the 2 yellow ones are true and the 2 blue ones are false, or the 2 blue ones are true and the 2 yellow ones are false. That is the conclusion you can draw by virtue of that continuous loop, which leads you to the exact same eliminations in those 2 columns, column 4 and column 7. Okay? All right, so now let's take a look at some real examples and some real puzzles. Okay, now with an X-wing or with any other fish, the base sets can be either in the rows or the columns. So here we have one on candidate 2 where the base sets are in the rows. And if you look carefully here in row 3, there's a conjugate pair right there. They're the only 2 2s in row 3. And then in row 7, these are the only 2 2s in row 7. And they line up perfectly to form a rectangle like that. There's your X-wing. So now, because these are the only 2 2s in those rows, that means you can eliminate every other 2 from the 2 columns containing those yellow cells. So we can eliminate that 2 and that 2, and over here in column 4 we can eliminate that 2 and that 2 and that 2. Okay? All right, next one. Okay, again we have one where the base sets are in the rows, and this is on candidate 9. Can you find it? I'll give you a couple of seconds. Okay, well, it's here in row 6 and in row 9. In row 6, those are the only 2 9s, the only 2 candidate 9s in row 6, and those are the only 2 candidate 9s in row 9. So we can eliminate all the 9s out of the columns. So there's one there, there's one there, and there's one there. So this time there are only 3 eliminations. Sometimes there's only 1, sometimes there's none, but there can be up to 14. Okay, next one. All right, this time the base sets are in the columns, and it's on candidate 3, and we have in column 1, we have a conjugate pair there, and in column 8, we have a conjugate pair there. So that means this time we can eliminate all the other candidate 3s from the rows containing the X-wing. So there's one there, there's one there, there's one there, one there, and one there, and one there. So there were 6 eliminations on that one. All right, next one. All right, again we have one with the base sets in the columns. In column 4, we have 2 candidate 2s, And in column 8, we have 2 candidate 2s. They're the only 2 2s in those 2 columns. So either the upper left and the lower right are true, or the lower left and the upper right are true, which means you can eliminate all the other candidate 2s from both of those rows containing the X-Wing. So you can eliminate that 2 and that 2, and you can eliminate that 2, that 2, and that 2. All right, let's go to the next one. Okay, for the rest of these examples, let's use the filters. So in this puzzle, we're going to turn the filter on for candidate 5, and let's see what happens. All right, if you look carefully, you see in column 3 and column 4, we have an X-Wing. So there are only 2 candidate 5s in column 3, and there are only 2 candidate 5s in column 4. And these filters help you see these a little bit better. Okay, so let's highlight them. Now don't forget the base sets are in the columns this time. And now what I'm going to do is I'm going to color the cells where the eliminations are possible. Because the base sets are in the columns, the eliminations are in the rows. So they're going to be here, 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 and here. That's where the candidate 5s in the rows containing those yellow cells lie. So we can eliminate that 5, and that 5, and that 5, and that 5. Okay? All right, let's go to the next one. Okay, let's take a look at row 3 and row 9. And take a look at candidate 1, and you'll see we have an X-Wing. So let's turn on the filters for candidate 1. And if you look carefully, you'll see that there are only 2 candidate 1s in row 3, and there are only 2 candidate 1s in row 9. And here they are. Those are your base sets, the 2 rows. So that means we can make eliminations in both of those columns. And don't forget, these X-Wings will always form a rectangle or a perfect square. This one happens to be a perfect square because you can see there are exactly 5 cells in between all those 4 highlighted yellow cells. Now the eliminations this time are going to be made in the columns because the base sets are in the rows. And let's see, where are the candidate 1s in those 2 columns, which would be column 1 and column 7. So there's one here, 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 and there's one here, here, and here. So we can eliminate all those candidate 1s out of those red colored cells. I'm doing that right now, but now I want to do something else. Let's get rid of these colors. I want you to notice what the X-Wing looks like now. As you can see, we made all the eliminations. So now the candidate 1s are the only 2 1s in column 3 and in column 7. To start with, they were the only 2 1s in row 3 and row 9. But now that the eliminations are made, they're the only 2 1s in the columns as well. So if you see something like this in a puzzle and you identify it as an X-Wing, you will immediately see that there are no eliminations to be made because it's already cleaned out. Both the rows and the columns have no other instances of candidate 1 except for in the X-Wing cells, which are here, 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 and here. And I call this a dead fish because there's nothing you can do with it. And this will apply more to the swordfish and the jellyfish, but it applies to an X-Wing too because an X-Wing, as I mentioned earlier, is a fish. So when you see something like this and there are no eliminations to be made, you have to accept that and quickly move on because there's nothing more you can do. All right, let's go to the next one. Okay, let's turn on the filter for candidate 8 in this puzzle. And we see that in column 5 and in column 7, we have 2 conjugate pairs on the 8s. The first one is here in column 5, the only 2 8s in column 5, and here in column 7, the only 2 8s in column 7. So now we're going to make the eliminations in the rows because the base sets are in the columns. And boy, there's a lot here. There are, looks like 9 eliminations are going to be made here. 1, 2, 3, 4, 5, 6, 7, 8, 9. So you can eliminate the candidate 8 out of all of those red cells. 1, 2, 3, 4, 5, 6, 7, 8, 9. And as I said, there can be up to 14 eliminations with an X-Wing. All right, let's go to the next one. Okay, lastly, we have an X-Wing where the base sets are in the rows and it's on candidate 5. So let's light them up. And we see that in row 1, we have 2 5s, and in row 8, we have 2 5s, and they line up perfectly to form our famous rectangle, which is called an X-Wing. So we know that because the base sets are in the rows, one of the diagonal pairs has to be true, either the upper left and the lower right, or the lower left and the upper right must be true. Therefore, we can eliminate all other candidate 5s in those two columns, in column 1 and in column 5. And so where are they? They're here, 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 and here. And they are here, 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 and here. So we can eliminate the candidate 5s from all of those red cells. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is a very common but powerful technique, and you will see these pop up all the time in puzzles of any difficulty level. Okay, so that's about it for today. We'll do some more examples of these basic X-Wings in video number 11A. There's not going to be an adjunct to this video. I'm going to wait until we do the video on finned and sashimi X-Wings, which will be the next video, video number 11. So let's go back outside and finish up. X-Wings are a very commonly occurring pattern that are not too difficult to identify. And what's great about them is that they can provide up to 14 eliminations at once. So you should keep an eye out for them at all times because you never know when one will pop up. In the next video, video number 11, we will learn how slightly imperfect X-Wings can still produce eliminations if certain requirements are met. These imperfect X-Wings come in 2 types, finned and sashimi, in keeping with the fish terminology. And then in video 11A, I will show you numerous examples of all 3 types of X-Wings, basic, finned, and sashimi. So thanks for watching, and I'll see you next time. Until then, be well and be happy.